Okay, 8.6 part 2. We're still talking about solving exponential and logarithmic equations. Example 3 is again a example of taking a logarithm of each side. So just like what we did in example 2, we're going to take the logarithm of each side. However, this one's slightly more complex. So the first thing that we have to do is we have to get rid of this additional constant over here on the left-hand side. We want it to just where we have a base with a single exponent. In this case, our single exponent is 5x minus 2. So we want to get that term by itself. So the first thing we do is subtract 2 from both sides. So that's 3 to the 5x minus 2 equals 4. So now I can take the log of both sides. Well, in order to cancel this 3 over here as a base and get the 5x minus 2 on its own, I'm going to take log base 3 of both sides. So log base 3 of 3 to the 5x minus 2 equals log base 3 of 4. And make that look a little neater. Okay, so that brings down our exponent on the left-hand side, so 5x minus 2 equals log base 3 of 4. And so now I need to try and get my x by itself the traditional way. So I'm going to add 2 to both sides. So 5x equals log base 3 of 4 plus 2. And then the last thing I do to get rid of the 5 is multiply both sides by 1/5. Okay, so I get x equals log base 3 of 4 plus 2 over 5. And there's a lot of stuff that I need to plug in on a calculator here. I can either do the log base 3 of 4 on a graphing calculator, because TI-84 will handle that, and then add 2, and then divide that whole sum by 5. Or I could change this to common logs using the change of base formula, so that would be log of 4 divided by log of 3, then add the 2, then finally divide the whole thing by 5. And no matter how I choose to do that, I'm going to get approximately 0.65. This is a very rough approximation. So the solution is about 0.65. Now there's two ways that I can check that. Okay. One way is I can do it algebraically. The other way is I can check it graphically. Can't quite, well, yep, there we go. I can get the whole thing in there now. So the way that you would check it graphically is you would graph both sides of the equation. So in other words, on the TI-84 or whatever graphing calculator, you would do y equals 3 raised to the 5x minus 2. Okay, and that would give you your logarithmic curve here. That's this portion. Okay, and then you would graph the right-hand side of the equation, which would be y equals 6. Okay, and that's obviously just a straight horizontal line at y equals 6. And then your intersection here, okay, is about 2/3 of the way, a little closer to 0.65. So you're close enough there that you can reasonably estimate it that it's about 0.65. Okay, or you can look at your table of values on the TI-84. All right, so next we're going to move on to example 4. Okay, now in example 4, we're now solving a logarithmic equation. So before we were solving exponential equations by taking the logarithm of both sides. This time we're going to solve a logarithmic equation by what's called exponentiating both sides. So what we're going to do, actually for this one we have the same base on both sides. I lied, sorry. This one we're not going to have to even exponentiate because the base on both sides is 7. So we have log base 7 of 3x minus 1 on the left, log base 7 of 2x plus 2 on the right. Well, when these two are the same, there's nothing else going on. You just have the log of some term and the log of some other term. And they have the same base, in this case base 7. Okay, but that could be anything as long as they are both the same. We can just assume that they're gone. Okay, so the same base property says that I can just take whatever we're taking the log of and set it equal to each other. So 3x minus 1 equals 2x plus 2. And I would solve that the traditional way. Start by adding 1 to both sides. It gives me 3x equals 2x plus 3. And then solve for x by subtracting 2x from both sides. It gives me x equals 3. So that means that my solution is 3. And I would check that algebraically by plugging back into the original equation. Okay, so I get log base 7 of, well, 3 times 3 is 9 minus 1, and then 2 times 3 is 6 plus 2. So that means now I have log base 7 of 8 on the left-hand side and log base 7 of 8 on the right-hand side, and sure enough, log base 7 of 8 is equal to log base 7 of 8. I should hope so. It's the exact same expression on both sides of the equation, so we're good.